In a wound rotor induction motor, the squirrel cage is replaced by rotor windings connected through slip rings to a series of external resistors. Adjusting the magnitude of the resistance determines the torque speed curve for the motor. The rotor of a wound rotor motor has more windings than the squirrel cage of a typical AC induction motor. The induced voltage in the rotor is higher and the current is lower. During startup, a typical rotor has 3 poles connected to the slip ring. Each pole is wired in series with a variable power resistor. The schematic diagram on the right shows the 3-phase AC voltages powering the stator windings and 3 variable resistors in series with the rotor windings. The resistor values are highest at startup in order to reduce the field strength at the stator, reduce the inrush current, and increase the torque. As the motor accelerates, the resistance is decreased to 0 at operating speed. Wound rotor motors are used in variable speed drive mechanisms for printing presses, rock crushers, and conveyors. Very high starting torque is needed in those machines, higher than you can get in a NEMA Type D motor. The graph on the right shows the effect of changing rotor resistance on torque in a wound rotor motor. The nominal torque speed curve is represented by resistance R0 in the green curve. Increasing resistance to R1 shifts the breakdown torque, shown in the red curve, from roughly 80% to 60% of synchronous speed. Increasing resistance to R2 decreases the starting current further to the point where the breakdown torque is equal to the starting torque at 300% of full load torque. This is shown in the blue curve. The shape of the curve for resistance R2 resembles that of the NEMA Type D motor, but that motor provides starting torque of only 275% of full load torque. Synchronous motors rotate at the synchronous speed, regardless of the load on the motor. In other words, the slip is 0. Large synchronous motors operate under 3-phase AC power. They have the same stator design as the basic AC induction motor. However, the rotor design is fundamentally different. The rotor contains electromagnets connected to a separate DC power supply. These magnets are stationary poles that attract to opposite poles of the stator, allowing the rotor to move in sync with the rotating stator magnetic field. The photo on the right shows the inside of a synchronous motor. The stator windings are closest to the yellow-colored enclosure, the same design of stator windings as for a 3-phase induction motor. But now the squirrel cage rotor has a different purpose. It is used solely to accelerate the rotor to synchronous speed because the copper rotor windings provide very little starting torque. You can see these copper windings closest to the center of the motor. There are a few other ways to accelerate the rotor to synchronous speed. You can use an external motor coupled to the motor drive shaft. Once the motor achieves synchronous speed, the external motor is shut off and the DC power to the rotor windings is turned on. You can also connect an external rheostat in series with the rotor windings, just like in a wound rotor motor. When the stator is excited, the synchronous motor starts like a wound rotor motor with similar high rotor winding resistance and high starting torque. When the motor nears synchronous speed, the resistance of the external rheostat is gradually reduced to 0. Once the motor is accelerated to synchronous speed by the squirrel cage rotor, the copper rotor windings are given DC voltage, pulling the rotor into synchronization with the rotating stator magnetic field. The relative motion between the squirrel cage rotor and the rotating magnetic field is reduced to 0. There is no induced EMF in the squirrel cage rotor, and it no longer has any effect on the circuit. Synchronous motors rotate at the synchronous speed, given by 120 times the line frequency divided by the number of pole pairs. Induction motors run at speeds reduced by the slip, with more energy lost in the rotor windings than in a synchronous motor. Hence, a synchronous motor is more energy efficient and is popular for very high-powered AC motors. On the other hand, a synchronous motor costs more to purchase than a comparable induction motor. So your choice of which one to purchase will depend on a precise calculation of the total cost of ownership over time. Synchronous motors are often found in mills and refineries, where large motor powers of 500 to 5,000 horsepower are common. That's 380 to 3,800 kilowatts, with motors of larger diameter than the heights of the people shown in the photo at the right. Small synchronous motors operating under single-phase AC power provide power to servo mechanisms which must run at very precise speeds. These motors are commonly found in critical aerospace guidance and navigation systems. Let's recap. Now you know how wound rotor and synchronous motors work. In the next video, we will teach you how single-phase AC motors work.